Okay, sure. Yeah, usually I give it at the end, but if you're not gonna be here, then yeah, you can pick it up. Yeah, I haven't posted yet, but I'll probably post it tomorrow. Yeah. Mhm.
I think they're already dead. I hope they don't come back, actually. They come back. Oh, yeah. I didn't put any. Yeah. I didn't come forward. I remember you came back and you're like, you did a job is helping us and we bring the phone for it. No, it me. You wasn't that. Oh, yeah, sure. Oh, she said it was me. Well, it doesn't matter. We both went there. We have to both to phone for it. And we got them. It was the rain, so. And most of them they were left outside of the rain. No one would read it. Like, I don't really go outside. I let everyone else do it. So. I don't really do work anymore. We had to try to get us to the bar. So I'm kind of just staying here. I'm waiting on this for here. I've done literally everything I can now. So if I do some work, it's like you should just find it. Yeah, you know. So you like to build with error. You like build with error. Basically. Very significant. I wanted to take it. Like that. I believe that. You want to see something sad?
Oh, sweet, I'm lying. This is your.
Also have one saying that, that's just like. Dr. Charlie, I'll get extra credit for being here, right?
I would have to take attendance if that were true, but that's
Let's do it then. Just for today. Just for today.
it's a lot of work. I don't like
We
taking
need to
attendance.
stick it out. I think it's fair, he's being. No, the rest are not really, this may be with.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to see everybody. All right, so first thing, probably you guys noticed Tuesday night, I did grade your midterm exam, so I do have them with me today. We'll probably end class maybe about 5 minutes early just so that you guys have a chance to pick them up. Average on the exam, you guys did pretty good. It was 37 out of 50. Pretty much right on the nose, 37, which is good, right? I will be posting solutions, so I have the solutions, they're in my office, so they're probably either going up tonight or tomorrow, depending on when I remember to do that. So you can check those out for your, just to kind of cross-reference with your exam, okay? A little bit how I graded, I kind of mentioned this maybe to a few people on Tuesday, but I graded, I mean, the final answer, of course, is important for these exams, but I more grade you guys on your process. Just because it kind of, I got the sense grading the exam that, time was an issue, and I think not everyone was able to kind of fully finish all the problems that they wanted to. So, if you were able to at least show me your process and kind of what you were thinking in terms of the equations you wanted to use and the process you wanted to use, I try to give you as much partial credit for that as I could. Okay. Same thing with the short answer questions as well, right? So it wasn't like a right or wrong thing, it was more just, like, are you guys understanding the information? And I think that goes beyond more than just whether you got the answer right or wrong. Okay. With that said, I do want to remind everyone about the grading policy in this class. So remember, we have 2 midterm exams. The second midterm exam is going to be not the week after we come back, but the week after we come back from spring break. And the 2 midterms are weighted differently. So one of the midterm exams is going to be worth 30% of your grade. The other midterm exam is going to be worth 20%. So whichever midterm that you score higher in, I'm going to count that as a higher weight. That's going to be worth 30%. And the other midterm that you score lower in, that's going to be worth 20%. And so if you did really well in this exam, then you can consider that, I would say that's always, money in the bank. And so, you already have that 30% kind of locked in. If you didn't do so well in this exam, you have the next exam to kind of really make up for it, to get the kind of grade that you. And of course, there's the final exam as well, which is worth 40%, which is a huge chunk of the grade as well. So if you didn't do so well, don't be discouraged. There's still a lot of points up for grabs, a lot of semester left to go. And there's definitely ways to make it up. Okay. All right. And so with that said, we are going to continue on with our discussion of convection today. So we are going to be continuing with external convection. I have a couple of examples that I wanted to do today with you guys. Just doing more of this, using the Nusselt numbers, picking the right correlation and going about it that way. Right. Homework 4 is posted. So homework 4 is all about this convection stuff. And so it is due, I believe, next Friday. So definitely you want to get started on it. After today, my plan is for you to be able to do everything that you need on the homework assignment. Okay. All right. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. And so on Tuesday, we were looking at external flow convection. Okay. And so external flow convection, this is situations where we have convection heat transfer. So in other words, we have a fluid that's flowing through the through our system. But these are situations where the boundary layer is allowed to grow unimpeded. Okay. Because whenever you have a situation where a fluid is striking a solid or flowing past a solid, there's always going to be a boundary layer that forms. So, for this case, we're looking at, cases where the boundary layer is going to keep growing, or there's nothing stopping it from growing. Okay. So kind of the classic example of this is a flow over a flat plate. Okay. So we have fluid flow that's coming towards the flat plate like this. A boundary layer is going to form just like that. Okay. And this fluid has a free stream velocity, a free stream temperature. Okay. And in these situations, we're often interested in how much heat loss or how much heat transfer is coming from the plate leaving to the fluid. Okay. Right. So we're interested in the Q that's coming off of the surface. And of course, we do have a way of computing this. So the way that we compute convection heat transfer traditionally is through Newton's law of cooling. And so we have H times A times the difference in temperature from the surface to the free stream. Okay. Okay. But of course, there's one, even though this formula here is quite simple, there is kind of one thing that's kind of complicating it. And it's the fact that, oftentimes we don't know, or it's part of the problem that we have to solve for this convection coefficient H. And so a big part of this entire unit is to kind of develop methods or to discuss different methods for solving for this convection coefficient, right? And so we went over that methodology last time, and we did an example of that as well. But let me just kind of summarize that for you. So step one, we have to identify the flow geometry. So every single flow geometry is going to have a different, kind of a different correlation or a different formula that we're going to use to solve for H. So that's kind of the first thing that you have to do. Okay. Right now, we only have one flow geometry. We just have flow over a flat plate, but we're going to introduce more geometries as we go along. Okay. Number two is we have to specify the film temperature for computing the fluid properties. Okay. Remember, a lot of the properties that we're going to use in our formulas here, they're very temperature dependent. And so things like the viscosity, the density, the Prandtl number, all of these depend on the specific temperature of the fluid that we are considering. And so it's important for us to specify that film temperature so that we can evaluate these fluid properties properly. Okay. And remember, the formula that we typically use, kind of the easiest one that we can do is simply just the average between the surface temperature and the free stream temperature. So TF here is going to be TS, which is the surface temperature of the solid, plus T infinity, the free stream temperature, divided by 2. Okay, and then based on that film temperature, you're going to look up the properties of the fluids in the corresponding tables or an online calculator in order to obtain their values. Okay, step 3. Once you have the fluid properties and you know the fluid velocity, you have everything you need to compute the Reynolds number. Okay. So remember, the Reynolds number is equal to U infinity times some characteristic length. Usually that length there is the length of the plate, at least for a flat plate, divided by the kinematic viscosity, which is what you looked up in step 2. Okay. And then depending on the value of the Reynolds number, that's going to tell you whether your flow is going to be laminar or if it's going to be turbulent, right? And so for less than 5 times 10 to the 5th, then this is laminar. Okay. But if we're greater than or equal to 5 times 10 to the 5th, we are turbulent. So we haven't discussed turbulence just yet or how that's going to affect our Nusselt number correlations, but that's going to be the first thing that we do today. Okay. Step 4 here is to select the appropriate Nusselt number correlation. This is kind of the key step because, we're going to go over lots of different formulas for the Nusselt number. And so you want to make sure you pick the right one. Question?
No,
Right.
thank you.
And then once you've selected the appropriate Nusselt correlation, step 5 is to finally compute the convection coefficient. Right? Because we know no matter which Nusselt correlation that you have, the Nusselt number is also equal to the convection coefficient multiplied by the length divided by the thermal conductivity of the fluid. Okay. And so if you solve for H is just equal to Nusselt number multiplied by KF divided by L. All right, so this kind of 5-step process, you're going to follow this, at least for the foreseeable future for computing the convection coefficient, right? And of course, the key step here is going to be step 4. Okay, I think part of the reason convection is, I think, confusing for people is that we're going to have so many different formulas that says NU is equal to something. Okay. And so I think it's very easy to get confused between all the different formulas for the Nusselt number that we're going to go over. But you have to remember that each of these formulas has specific conditions on which you should actually use them. Okay. All right. So far, we've only gone over one, right? So the only Nusselt number correlation we've gone over so far is 0.664 times the Reynolds number raised to the 1/2 power times Prandtl number to the 1/3 power. Okay. This is specifically only for cases when you have flow over a flat plate, and the flow is laminar. Okay. So today, we're going to introduce a couple more Nusselt number correlations, just kind of be aware of, the formulas themselves, of course, that's what you plug into, but you want to be aware of the conditions under which you can actually use that correlation. Okay, and I think that's kind of the main confusion with convections, that we're going to go over lots of these different Nusselt correlations. You want to make sure that you pick the right one. Okay, so that was just kind of a summary of what we talked about on Tuesday. Any questions on this so far? Okay, all right, so let's go over one of those other conditions. And so let's look at specifically, let's stay with the flat plate. So let's look at the flat plate under different conditions. Okay, so if you change the flow conditions, even some of the thermal conditions too on the flat plate, it can affect how your Nusselt number is computed. Okay, so let's start with turbulent flow. Okay. So if you remember from last week, remember we discussed how turbulent flow is often used, or the way that it affects heat transfer is that it often enhances heat transfer compared to laminar flow. Right? And so that's going to be reflected in our Nusselt number correlation as well. Okay. And so let's just let me just go ahead and state it. So the Nusselt number correlation for turbulent flow over a flat plate. Okay. So our flow geometry is the same. It's just that our flow conditions are different. Is 0.037 times Reynolds number raised to the 4/5 power times Prandtl number raised to the 1/3 power. Okay. Actually, I should append this. And so this is for a fully turbulent flow over a flat plate. And we'll go over kind of what that means in a second. Okay. Okay, so if you compare this formula, for the Nusselt number correlation compared to our laminar case, right? And so our laminar equation conveniently is right there, right? If you look at the coefficient in front, it may look like the second correlation is actually less, right? And so if you compare the 0.664 and the 0.037, just based on that, it looks like your Nusselt number for laminar flow is going to be 20 times higher than that for turbulent flow. Okay. But if you actually look at the coefficients here, or the exponents, the main difference between these correlations is that for turbulent flow, the Reynolds number is raised to the 4/5 power, as opposed to laminar flow, where the Reynolds number is only raised to the 1/2 power. Okay. And so what you should see, because of this change in the exponent, and because of the fact that turbulent flow, the Reynolds number is just naturally going to be higher, you should get a much higher Nusselt number for turbulent flow than you do for laminar flow. Okay, so that's what you should use for a turbulent boundary layer, right? And so we're gonna do an example of that later on. Okay, now I did add this kind of a modifier here for fully turbulent. So what does that mean? Okay. So to use this Nusselt number correlation, it assumes that the entire boundary layer, or you can say the majority of the boundary layer, has turbulent flow. Okay. So what does that mean? So in the absence of any kind of flow disturbances, and so if you have just kind of just regular parallel flow over a flat plate, there's actually a transition that the boundary layer actually undergoes. Okay, so for undisturbed flow, right? And so you don't have nothing there. So we're going to talk later about sometimes you may want to trip turbulence on purpose, and so you may add a turbulence trip wire. You may add a rough surface to kind of induce turbulent flow. But if you have kind of a perfectly smooth surface, undisturbed flow, the boundary layer actually starts out laminar and then transitions into turbulence. Okay. And so it kind of looks something like this. And so if we draw kind of a flat plate, we have flow that is coming at the boundary layer like this, okay? And so we're going to assume that this flow is undisturbed, so there's nothing kind of impeding the flow or nothing that's going to induce turbulence, okay? And so at first, the boundary layer is going to be laminar. And this always happens unless you trip it, okay? So there's always going to be kind of the front region of the boundary layer is always going to be laminar. And then usually at some other point, then the flow transitions into turbulence. And then once we kind of get to this, then the flow kind of gets more chaotic. And so this type of boundary layer where you have kind of a laminar region and a turbulent region, and let's say that they are roughly about the same, we call this a mixed boundary layer. Okay. And so a mixed boundary layer has another Nusselt number correlation. Okay. So this correlation kind of accounts for the fact that we have a laminar region and a turbulent region, and the heat transfer characteristics are going to be different in the laminar and the turbulent regions. Okay. So this correlation looks like the following. It's a little bit more involved. Okay. And so it's going to be parentheses 0.037 times Reynolds number to the 4/5 power. Okay. So that's the contribution from the turbulent portion. Okay. But we have to adjust this. We have to subtract out, the fact that this laminar, this boundary layer starts out laminar. Okay. And so luckily, or maybe unluckily, that this number is kind of a fixed number. So it's 871.323, kind of a very random number. Okay. And then you multiply this by Prandtl number to the 1/3. Okay. Okay. And so if you look at this formula compared to the fully turbulent boundary layer, you can see that the only difference is kind of we're subtracting this term, okay? And so all this term here does is that this term is an adjustment based on the laminar region of that boundary layer. Okay. And so technically speaking, unless you have something where the problem tells you or the situation tells you that you have some kind of rough surface where you're purposely tripping turbulence, technically this formula here is the more correct one to use. Okay. This number can be hard to remember. Honestly, I always forget it. That's why I have it written down. And a lot of times, you'll have a case where your boundary layer is 99% turbulent anyway. And so, it probably won't matter which one that you use, but if you want to be technically correct, this one is a little bit more precise, especially in those types of boundary layers that are kind of transitional, that are kind of close to that threshold. Okay. Questions?
Well, when we have a fully turbulent flow,
Mhm.
would that be told to us, or will we have to determine that with the Reynolds number?
Yeah. So so the way there's usually two different cases for this. And so there are cases where your Reynolds number may be just exceptionally high. Like it might be like, something on the order of 10 to the 7th power. And so in that case, you can assume that the boundary is fully turbulent because the Reynolds number is so high. There might be other cases where the problem will tell you where the geometry added like tripwire or some kind of rough surface to purposely trip turbulence.
Okay.
And so in those cases, in that case, you can assume you have a fully turbulent boundary layer as well.
So like, we know that a flow can't just all of a sudden go from laminar to turbulent. So say, for example, if we were to get a Reynolds number that was computed to be 5 times 10 to the 5th, can we assume that that's a mixed boundary layer?
Yes. Yeah. So for cases where the Reynolds number is pretty close to that threshold, I would definitely use this formula here. Just because it's, you have more transitional flow than turbulent. But yeah, it kind of depends on the value of the Reynolds number.
Okay.
Yeah.
Thank you.
Mhm. Yeah. Great question. Another interesting thing, I think I think the homework actually asked this as well, is you can actually locate approximately where in the boundary layer the flow actually transitions to turbulence. Okay. And so this can be useful for determining, exactly how much of your boundary layer is turbulent or not. Okay. So we know that the flow transitions to turbulence when the Reynolds number reaches 5 times 10 to the 5th, right? That's kind of the magic number for external flow, right? And so if you have flow over a flat plate, you can actually set this equal to, the Reynolds number itself. So U infinity divided by the viscosity, okay? But instead of plugging in the total length of your plate, you can instead solve for some location X, where this X right here, right? If you set the Reynolds number exactly equal to 5 times 10 to the 5th, you can compute the exact location X where that transition occurs. And so if we just rearrange this, we have X is equal to 5 times 10 to the 5th multiplied by viscosity divided by U infinity. Okay. And so sometimes we call this X sub C. So X sub C here, that is the critical length where turbulence occurs. All right, so sometimes what I like to do, sometimes it's very obvious where your Reynolds number is, extremely high. But if you're not sure how much of your boundary layer is turbulent, what you can do is you can take the ratio. You can take the ratio of this critical XC divided by L. It's C, excuse me. Yeah, sorry about that. The C stands for critical. Yeah. And so if you take the ratio between the critical length and the total length of your plate, what this will show you here is that this will show you the percentage of your surface that has a laminar boundary layer. Okay. And if this percentage is anywhere between 1 to 5%, I would just assume that the whole thing is turbulent. Okay. There's no actual number for that, but that's just kind of my own approximation. Right? But if you can always remember this number, if you can always remember the number 871.323, then you can just use that format there. But I have a hard time remembering this number, and so a lot of times if I can, I just assume that the boundary layer is completely turbulent. Okay. Any questions on this? Okay. All right, so there's one more Nusselt correlation that I want to go over before we do our next example. Okay. This one is a little bit more niche, and so this one I honestly I don't use it all too much. But for cases where the thermal condition at the plate is different, then that does actually change your Nusselt number correlation as well. Because technically, the thermal condition at the plate, that's going to affect your thermal boundary layer production. And so, that's going to affect things. So what do I mean by the thermal condition? So far, we've essentially assumed that the plate is at a uniform temperature. So the entire plate is the same temperature throughout. So in other words, there's just one surface temperature on the plate, and that surface temperature goes throughout the entire plate. Okay. But there's a lot of situations where that's not true, right? And so if you think about, our fins, right? So one of the hallmarks of fins and extended surfaces is that, you have a much higher temperature near the base of the fin and a much lower temperature at the end. And so that assumption here of the plate being all the same temperature is probably not going to be appropriate in that case. Okay. So we can adjust our Nusselt number correlation for cases when our plate may not have a uniform temperature, but maybe has a uniform heat flux throughout the entire plate. So this Nusselt correlation would be more appropriate for like a fin, where we know the temperature is going to change throughout the length of the fin, right? But probably it's more appropriate to say that the heat flux is going to be more uniform throughout. Okay. Then our Nusselt number correlation is 0.68 times the Reynolds number to the 1/2 power times Prandtl number to the 1/3. And this is specifically for laminar flow. Question, yes.
How do we know when it's like, when you use this one, like, besides just like, tell us it's more heat flux, is that the only thing that helps?
Yeah, so honestly, for most practical situations, it's gonna be kind of neither. It's gonna be neither a uniform temperature or a uniform heat flux. It's gonna be somewhere in between. It's very hard to get a physical situation to obey that exact thing, but usually it's gonna be closer to one or the other. So usually, if for most of my cases, I would lend more towards the size of uniform temperature. That's going to be the more common case. It's only really if you have like a really long kind of surface where you have a huge temperature difference from one end to the other, then that's where this one would be more appropriate. But generally for this class, I will tell you in the problem which one to use. Yeah. Mm-hmm. And actually, these formulas aren't all that different. And so if you actually compare this one to our other one from above, right? So this is the one that we used yesterday. The only difference is in the coefficient out in front right here. And so instead of 0.664, we have 0.68, which is practically the same. So if you're gonna remember one formula, I would remember the other one. But technically there are differences. And for other geometries, there's gonna be bigger differences based on the thermal conditions. We're not gonna go through a lot of those in this class, but I just wanted to show you that it can change. Okay. For turbulent flow, if you have turbulent flow over a plate with uniform heat flux, in that case, the fluid conditions, the turbulence kind of dominates everything. And so for turbulent flow, you can just use this formula here, either the mixed boundary layer or the fully turbulent boundary layer. So, in turbulent flow, the differences are even more small between the two. Okay, but I did want to mention this, not something that we're going to use a lot in this class, just because the differences oftentimes are going to be really small, but there can be differences if you're going to dive deeper into this stuff, maybe in graduate school or something like that. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example. Okay, so actually let's consider a fin. And this fin, we'll say, is responsible for cooling a computer. Okay. And so if you've ever looked inside a computer, all these computers have some kind of fan that's meant to circulate air or blow air. Okay. So we're going to be looking at forced convection from a fan to cool a computer. Okay, so we have, let's say our computer surface is a flat plate, because that's all that we know how to do so far. Let's say we have a fan over here. So let's say our fan is rotating and it's blowing air across the surface of our computer. Okay. Okay. So let's say that this air is slightly cooler than room temperature. So we'll say the air has a temperature of 20 degrees C. Okay. We'll say the length of this plate is only 10 centimeters. Okay. So even though it's a fin, it's a fairly small fin. And so what we're actually going to assume is that we're going to assume that this fin is at the same temperature all throughout. Okay. And just for purposes of calculations so we can compute the surface area, we'll say that this fin has a width into the page of 5 centimeters. Okay. So the surface temperature in this case, we're going to say is 45 degrees C. Okay, so we're gonna say our surface temperature. Okay. So we want to maintain a surface temperature of 45 degrees C on this computer, okay? And we're going to assume that the amount of heat that the computer is giving off is equal to 5 watts. Okay. So that's how much power that we have to offload into the environment. Okay. We want to find out. So basically, in this situation, we're actually designing our fan, right? And so, we've kind of already built our system. We've designed it to run, the top shelf games on ultra high, graphics. And so we want to make sure that our fan is producing adequate airflow to cool our computer. Okay. In particular, we want to find out, what the fluid velocity should be in order for us to maintain these conditions. Okay. So a little bit of a backwards problem. So, it's quite different than the ones that we did on Tuesday, right? So in this case, we're actually solving for what the fluid velocity is going to be. Okay. But the process that we're going to follow is still the same. So we're still going to, follow through with our convection problem solving methodology. It's just that the velocity is actually what we're going to be solving for. Okay. Okay. Any questions on the setup for the problem? Okay. All right. So let's start this problem by using our convection problem solving methodology. Or let's get as far as we can, because we don't have the velocity, so we actually can't compute the Reynolds number, but we can actually get quite far. Okay. So step one is to identify the flow geometry. So this is pretty straightforward in this case. We have flow over a flat plate. Okay. Easy peasy. Which is good because that's the only geometry we know so far. All right, so step two in our methodology is we need to compute the film temperature. So we need to compute the basically the temperature at which we're going to evaluate the fluid properties. Okay. Okay, so we can do that in this case because we have a surface temperature, we have a temperature of the freeze stream, and so let's go ahead and compute TF. And so TF here is going to be the sum of T infinity plus TS divided by 2. Okay. So we know T infinity in this case is 20 degrees C. Our surface temperature here is 45 degrees C, so we divide that by 2. We get 32.5 degrees C. Okay. All right, and so if you use this temperature here, you refer to the table in the book. So this is either table A4. Okay, so that's going to be the properties of air at specific temperatures. Or if you want to use a calculator, that's fine too. Okay. So there's online calculators. If we have time after class, I'll show you what that looks like. And so if we evaluate it at that temperature, we would get a kinematic viscosity of 15.89 times 10 to the minus 6 meters squared per second. We have a thermal conductivity of the fluid equal to 26.3 times 10 to the minus 3 watts per meter Kelvin. And our Prandtl number in this case is 0.707. Okay, so those properties are going to be important for us moving forward. Okay. The next step in our convection methodology here is to compute the Reynolds number to determine whether we have turbulent or laminar flow. Okay. So the Reynolds number, our formula for the Reynolds number is U infinity multiplied by the length of the plate divided by the kinematic viscosity. Okay. Unfortunately, of course, we can't compute this just yet because we don't know the fluid velocity. In fact, that's what we're solving for. So we're gonna have to leave this as it is right now. But before we move forward, just because in step 4, we need to actually, compute the Nusselt number, we do need to make an assumption on this. Okay. Because that's going to affect the Nusselt number correlation that we select, which is also going to affect the convection coefficient that we compute as well. Okay. Okay. Now, of course, we, in situations like this, if you know a bit about your system that about the length scales and stuff like that, the typical velocities, you can make a more informed assumption here. If you don't, of course, you're kind of just shooting in the dark a little bit. You kind of have to pick one. But what you can do in these situations that you can solve the problem, you can pick one, solve the problem, and then go back and check later whether your assumption was correct or not. Okay, so we may need to go back and check to see if our assumption is correct. So we'll just leave a note for that here now, and then we'll actually go back and check it later. Okay. For now, let's assume laminar flow. Okay. The reason I would pick laminar flow in this case is because the length scales are quite small. So we're talking about just the flow over just a very small computer. So our length scale is only 10 centimeters. And we're not putting a jet engine inside our computer. This is a little dinky kind of plastic fan. And so I don't expect the velocities to be all that high. And so, I think our assumption of laminar flow is pretty justified in this case, but we'll go back and kind of check later on. Okay. Step 4. Step 4 is to select the appropriate Nusselt correlation. And so for laminar flow over a flat plate, we have, with the constant surface temperature, we have our Nusselt correlation for that. Okay. So the Nusselt correlation in this case is 0.664 times Reynolds number to the 1/2, Prandtl number to the 1/3. Okay. All right, and so once we have, now that we've selected our appropriate Nusselt correlation, step 5 is to compute the convection coefficient. Okay. And so we know the Nusselt number is equal to H times L divided by KF. Okay. And so if we set that equal to the correlation that we have above, 0.664, Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay. Let's solve this equation for H. And so if we solve this equation for H, we get H is equal to KF divided by L. Let me clean up that K. Times 0.664, Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay. Now we have everything in this expression here except for the Reynolds number because we don't know the velocity. What you're going to see, we're actually going to kind of back compute it. Okay. But at least at this point, we have an expression for the convection coefficient, that we can kind of use in our other equations. Okay. All right. Any questions on how we got to this point in the example here? Okay, good. All right. So for a kind of a typical problem, this is kind of where, we'd be able to plug in and solve for H. But since we don't know Reynolds number for this example, we're going to just kind of operate with under this assumption right here. Okay. Okay, so let's go back to the problem. Okay. And so if we go back to the problem, let me kind of scroll up here so you can see. Okay. We have a situation where we have airflow that's going over a computer. Okay. In this case, for this problem, we know exactly what the surface temperature of the computer is. So we know the surface temperature is 45 degrees C. We know the free stream temperature of the fluid. So the fluid we know is 20 degrees C. And in this case, kind of very uniquely, we actually know how much heat that the computer is actually giving off, right? So we know Q, we know TS, and we know T infinity. Okay. We can actually relate all these things, right? So, a formula that actually relates all three of these quantities is Newton's law of cooling. Okay. And so we know that Q for convection is equal to H times A times TS minus T infinity. Okay. So let's bring that relationship down to the bottom, and let's use that to solve eventually for the fluid velocity, right? Because what do we have? We have an expression for H, right? So we know that H is going to be a function of the Reynolds number, which is a function of the velocity. And so we can kind of eventually plug everything back in and eventually solve for the velocity from this expression right here. Okay, so if we have Q is equal to H times A times TS minus T infinity, right? Let's take this expression for H that we found out from before and plug that in right here, okay? I'm going to go ahead and plug in for A as well because we have a rectangular plate. So A is nothing more than just the length times the width, okay? And so we have Q is equal to, we plug in for H, we have KF over L times 0.664 Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay. Let me put square brackets around this just to make it a bit neater. The area is the length times the width. Okay. And that's going to be multiplied by the temperature difference, Ts minus T infinity. Okay. So it's a little bit of a mess, especially with the decimal there. It's a bit of a mess. But let's take this expression and let's solve for the only unknown here, which is the Reynolds number. Okay. All right. So if we solve for that, let's see. So we're going to be dividing by a lot of stuff here. So we have Q divided by KF over L times 0.664 times Prandtl number, the 1/3, times L times W times TS minus T infinity. Okay. All that's equal to Reynolds number to the 1/2. Okay. We can simplify this. These L's are going to cancel out here. Okay. Some of you may have noticed that already. Okay. I was wondering where it went to my solutions. Okay. Okay, so everything on the left-hand side that we can actually kind of plug in, we know kind of what that is, okay? So if we plug in everything there and we square it, okay? So everything on the left-hand side was either given to us in the problem or it's a fluid property that we looked up in the table. And so in that case, we can compute the Reynolds number. And so the Reynolds number in this case is 6.61 times 10 to the 4th power. Which, if you remember, in order to get to this point, we had to make the assumption that our flow was laminar. And so let's go ahead and confirm that our flow is indeed laminar. So since this Reynolds number here that we computed is less than 5 times 10 to the 5th, this confirms our assumption that our flow is indeed laminar. Okay. So that's good. So that means we can continue. But let's say that you solved this problem and you assumed initially that the flow was turbulent, but then you found the flow is laminar, then you would just kind of redo the problem and just kind of change that assumption from the beginning, okay? Sometimes with these convection problems, just because of the way the correlations are designed, sometimes you're gonna have to do a little bit of guess and check. That's okay. Just kind of make sure that you're kind of aware of that, okay? Okay, and now that we have the Reynolds number, we can use the Reynolds number to actually solve for the velocity. Okay. So the Reynolds number we know is equal to U infinity times the length of the plate divided by the kinematic viscosity. Okay. And so if we solve for the velocity here, U infinity is equal to Reynolds number times the kinematic viscosity divided by L. Okay. We plug everything in, so we know the viscosity from the fluid properties that we looked up in step 2. We know the length of the plate. We just solve for the Reynolds number, and so the fluid velocity in this case is 10.5 meters per second. Okay. Which is not insignificant. That's actually a pretty decent speed. And so, in order to kind of keep your computer cool, sounds like you need a pretty powerful fan in order to get that to work. Okay. So I know there was kind of a lot involved with that example, but I think it's a good example of kind of some creative things that you can do with these convection type of products, okay? And this is something that's really practical too. So this is kind of, directly applied to kind of thermal design of a system. And then based on the speed, then you're going to know exactly what fan that you're going to use or which fan to order to kind of for your rig. All right, any questions on this example here? Okay, good. So we have a little bit of time left. So I do still plan on ending the lecture a bit early. But let me introduce kind of the next thing. And then we'll do one last example on Tuesday to kind of finish up this section. Okay. So let's introduce another type of flow geometry that's common for external flow, which is flow past a cylinder, or oftentimes flow past a blunt body. Okay. So I'm going to use a cylinder, although, these correlations that we're going to go over kind of work for almost any blunt body, but a cylinder is just easiest to draw, okay? So we'll say the cylinder has a diameter D. Okay. We have flow that is coming at it. Okay. And so, of course, this flow has a velocity U infinity. Okay. All right. So the flow past the cylinder is actually quite interesting, because, the flow has to go around the cylinder, right? You can't just phase through it. It has to kind of go around the solid object. So there's always going to be a portion of your boundary layer here where we say the boundary layer is attached to your solid. Okay. And so usually on the upstream side of your geometry here, you're going to have that boundary layer be attached. But eventually, because of the nature of this geometry, there's going to be a portion of where the boundary layer actually separates from the object. Okay. And so there's going to be a point where the boundary layer actually comes off or we say separates from the body itself. And so what that does is that creates a region on the back end of your body here, that we call the wake region. Okay. Right. And so what's unique about the wake region is that it presents kind of very unique fluid mechanics. And so the kind of the flow patterns and the flow velocities and the pressures in the wake region are very different compared to the boundary layer. Okay. Okay. And so, of course, if it's going to affect the flow patterns, it's also going to affect your convection heat transfer as well. Okay. And so we have kind of three different types of flow, I would say, conditions on the surface that we need to account for in a blunt body. So the first type is kind of the same as our flat plate. We have laminar boundary layers. Okay. Number two, we have a turbulent boundary layer. So those two things are the same. So as same as the flat plate. So, just because you have a blunt body, you're still going to have you'll still have laminar boundary layers, turbulent boundary layers. But what's unique about the blunt body is that we also have to consider the wake region, which is going to have, like I said, unique fluid mechanics. Okay. So, I'm not going to get too much into the fluid mechanics of flow over a blunt body. That's kind of more of a topic for 333. But for our purposes, what we're mostly interested in from a thermal perspective is how much or how big each region is going to be for our given geometry. And so what you're going to see is that, for flow over a blunt body, we actually going to go by a little bit different rules. And so, there's not a strict cutoff between laminar and turbulent like there is for the flat plate. There's a lot of different regimes because within the different regimes, you're going to have different sizes of these regions. Okay. Any questions on this? Okay, so let's I'm going to draw you a couple pictures here just to kind of show you what these might look like. Okay. So let's look at a case where we have very laminar flow, so very gentle, very slow flow. Okay, so let me go ahead and draw my cylinder. We have the velocity that's coming at it. Okay, so this is not the most extreme case. And so in the extreme case, you can have what's called creeping flow. And so creeping flow is flow that's so slow, or maybe the fluid is just so viscous that no boundary layer separation actually occurs. So it is actually possible to have flow past a blunt object and have the boundary layer stay attached the entire time, but the flow has to be extremely slow for that to happen. Okay. So what's more common, even for our laminar case, might be look something like this. Okay. So, when I'm talking about flow past a blunt body, I'm going to talk about, the upstream side. Okay. So the upstream side of the object is the part of the object that's going to be meeting the flow. That's the part that's going to be hit by the fluid first. And then the downstream region is going to be the part where the flow, eventually goes towards. Okay. So in most cases, your upstream case, you're going to have a stagnation point. Okay. So you're going to have a point where the flow kind of stagnates right in the middle right here. Okay. And then the boundary layer is actually going to start to wrap around from the stagnation point around the object. Okay. All right. So for laminar flow right here, we have a laminar boundary layer that stays attached to the object on the upstream side. Okay. But when you have laminar flow, the boundary layer eventually is going to separate from the object itself. Okay. And what's interesting is that because the flow is fairly slow, separation actually occurs fairly early. And so the separation occurs kind of maybe around this region right here, kind of when you get to the top of the cylinder. And so your flow kind of looks something like this. And so with laminar flow, you have fairly early separation of the boundary layer. Okay. So now let's look at a case where our flow has a bit more velocity. And so let's say we have more turbulent flow here, okay? And again, these are not two, these are not kind of, two different cases. These cases here kind of exist on a spectrum. And so depending on the Reynolds number of the flow, depending on, the speed and the size of the object, you may get cases anywhere in between these two. Okay? Okay, so for a case where our fluid has more speed, we have velocity coming in. Okay. We have a stagnation point just like before. And just like before, we're going to have a region where we have a laminar boundary layer that's attached to our object. Okay. But when our flow has more energy, or when our flow has more speed, that boundary layer is actually going to transition into turbulence somewhere along the length of the object itself. Okay. So we have right here the boundary layer transitions to turbulent. Okay. So you have kind of a rougher boundary layer there. But what's interesting is that when you make the flow more turbulent, the boundary layer actually stays attached for longer. And so you have kind of a late separation kind of down here. Okay. And so you still get separation with turbulent flow. It's just that it happens much later. And that results in a much smaller wake region. Compared to the laminar case. Okay. Okay. So we'll pause here for now. And so we'll talk about on Tuesday how this affects our Nusselt number and how that affects our calculations. And we'll do an example with that. Okay. But I did want to end lecture a bit early to give you guys time to pass back your exams. So you guys can come up and grab your exams. So they're just all in just one big pile, so you can just kind of find your name. Remember, the average on the exam was 37 out of 50. So it's kind of right on the nose right there, which is good. If you're on Zoom, I'll bring the exams again on Tuesday so you can pick it up then. All right. But thank you guys for coming this week. Hope you guys have a good weekend, and I will see you guys on Tuesday.
Dr. Graham.
Yeah.
Thank you for giving points for being on time today.
Of course.
Yeah.
All right, now you're being petty.
Okay.
There's traffic on that side.
Traffic,
Yeah, I think yours is right here. Thanks, Clint. Big pile.